This session is ICSCorsair, how I will pwn your ERP through 4 to 20 milliamp current loop by Alexander Boyshev and Gleb Cherbov, who is not able to make it to this presentation, but we wanted to give him credit. So please welcome Alexander.
Okay, thank you. Today I want to talk a bit about low-level protocol security and how to control and pound your ICS infrastructure through the low-level protocols and what tools do you need to do this. My name is Alexander Bolshev and I work as an information systems, especially ICS auditor at Digital Security. I hold PhD and also work as assistant professor at St. Petersburg State Electrotechnical University. My research area is distributed system security, and I'm yet another man wearing some color hat. I made this research with the great help of my colleague, Gleb Cherbov, but unfortunately he could not get a US visa. It's a pity. He also works at Digital Security as an information security researcher. Okay, here is the small agenda for the presentation. At first I will show you a demo, then I will introduce you in some details of modern ICS infrastructure on low levels, and after that we will talk about ICSCorsair board that I've been developed to hack low-level protocols and its features. After that, I will show you some vulnerabilities that we have found and possible attacks that could be done with the board. And Captain Obvious reporting conclusion will finish the talk. Here should be a really cool live demo, but Russian and US customs were really against it. For live demo, I would have to bring here industrial transmitter and power source, but they have heavy steel cases, so carrying across both borders with them in current political situation might be a bit risky. But I've been prepared and recorded a video demo. Before I show you a video, I should say a few words about DIMM infrastructure. Here we have Honeywell XNX gas analyzer transmitter that connected to plant asset management software, especially field care, using USB hard modem. PAS is getting industrial process state information from the transmitter, accumulates it, and periodically sends to the enterprise resource planning software. In our case, it's SAP. The channel between corporate and an industrial network is divided by firewall that allows only HTTP traffic to pass. Okay, video demo how to hack SAP through the hard transmitter through the analog protocol. Here is my lab, and you can see the hard transmitter. It's without case. It's a gas analyzer. It's a hard modem, and you could see the hard signal on the oscilloscope. And this is field care software. You could see it shows some parameters that it's getting from the transmitter. For example, current in the current loop in milliamperes, and the field engineer will see this information on his display. And you could see that the SAP software is in the neighbor network and it's reachable by the HTTP. This is our attack machine. It's running Kali, and here we have Netcat that listening to 4444 port and special Metasploit modular for attacking. And now this is the ICSCorsair board. I'm connecting it to the hard line. The hard current loop is a pair of copper wires, and in reality to make the attack you don't need to intercept it or cut off. You just need to connect the pair of wires in parallel. For example, you can use a pair of sewing needles solder it with copper wires. And now I just connect it with lab connector. The ICSCorsair is connected to the attack machine with USB. Oops, this is wrong USB port. In a second it will be corrected to the FTTI CM1. And now model is started and something strange now happening on the line. You could see the strange sinusoid with very high amplitude, and it's a jamming signal. I'm jamming the hard line to intercept any communication in the line. You can see that hard modem is getting crazy, a bit crazy after this signal. And as you can see, it's communication fault, communication error on the field care screen. And what will be the typical ordinary reaction of ICS engineer in such situation when he will see this mess? He will stop, disconnect the device from the network programmably, and will try to verify the network, verify network state. And he is starting to verify the network, and in a moment the shell will appear in our machine. Here it is. We have shell on the SAP server. It's like a magic. We have sub-server credentials, so we can do almost anything. And you can see that the IP of the server is that server that could be reached from the PAS server. Here it is. And here it is. Okay. Let's return to the presentation. Now you are probably asking a question, how is it possible? What's the magic happened? The answer is really simple, modern industrial control system architectures. I will try to explain it now. Now it's a short but bit boring part of the talk, where I'll try to quickly introduce you to current state of ICS, low-level protocols 101, and other things. Today, ICS industrial control system infrastructures are commonly used in every factory and even in your house. The ICS tools collect data from the remote stations, also called field devices, transmitters, or remote transmission units, R2s, processes it, and uses automated algorithms or operator-driven supervisory to create commands to be sent back to the field devices. The typical ICS infrastructure is shown on the slide. Here we have the low-level devices, such as field devices and programmable logic controllers. We have medium-level devices, such as SCADA, DCS, that gating data from the low levels and sending commands back. The field devices do all dirty work by interfacing objects in the real world, in the real physical world, for example, controlling water pump or monitoring temperature in reactor. And on the higher level of infrastructure, you have manufacturing execution systems and ERP systems that connect our ICS infrastructure with business processes. But if you look inside this infrastructure, you'll find many familiar terms such as Windows operation systems, Linux operation systems, and such technologies as Ethernet, TCP/IP, HTTP, XML, DCOM, .NET, SOAP, SQL, maybe NoSQL, it's also possible, and others. The another question you can ask right now, how this dirty mess of multiple layer hardware, multiple software systems, and mess of technologies may work at all. The answer is simple, deep integration. And as you may know, deep integration always leads to deep trust. The most weak point of such infrastructure is a set of low-level industrial protocols that flows in the industrial buses. The protocols connect intelligent field devices with PLCs, SCADA, PAS, and other systems. And most of such protocols were developed in the previous century. Of course, they provide no authentication, no authorization, no cryptography. And based on deep integration and trust, upper system doesn't expect anything bad from a field device. You can see several field devices on this slide. The transmitter that I have used in the DIMA is on the left. It looks a bit different inside the case, but it's that transmitter. And these field devices intend to measure temperature, pressure, gas presence, and other parameters. Different field protocols flow in the industrial buses. For example, HART, that was in a DIMA that works over current loop, 4 to 20 milliamperes. Profibus DP and Modbus that could use RS-485 physical layer, and many Manchester bus-powered protocols such as Profibus PA and Fundamentation Field Bus H1. I should say a short introduction to Highway Addressable Remote Transducer Protocol, HART. It was developed by Rosemount in mid-1980. It's mostly used on power plants, chemical factories, oil and gas industry, so it's primarily intended for hazardous environments. Current loop length can reach up to 3 kilometers, and HART transmitters often placed out of the plant building, for example, for controlling environment, monitoring presence of toxic elements in the air, and other parameters. HART uses half duplex master-slave scheme and works over 2,200 Hz frequency and has 1,200 baud speed. Of course, there are no authentication, no authorization, and no cryptography. In this picture, you can see how HART frequency shift keying works. HART signal modulated over analog current loop signal in a range of 420 milliamperes. Protocols work in master-slave mode. Master sends a command, and slave device responses with a reply. There are, according to HART standard, of course, no more than 2 masters on the line, and 1 bit is modulated with 1,200 Hz, and 0 is modulated with 2,200 Hz. The example FSK transmission captured by oscilloscope is shown on this slide. You can see the sequences of zeros and ones. The sequences of zeros has high frequency. And example HART network scheme is shown here. For creating current loop communication line, you just need 2 copper wires. In reality, it's also the same. And as I've said earlier, the length of these wires could be up to 3 kilometers long. Also, many transmitters could use the same wires for power and for communications. In this talk, there will be shown no vulnerabilities of low-level protocols based on RS-485. However, the board that I have developed, ICSCorsair, supports working with Modbus and Profibus, so I should mention these protocols here. Modbus is a very old protocol. It could work over RS-485. Mainly in Russia, we have many devices based on Modbus working over RS-485. And in most cases, it has no authentication, authorization, or cryptography. Profibus DP is a protocol that has been developed as a replacement for all field protocols. It also works above RS-485 and has hybrid medium access method using token and master-slave scheme. So why do we need yet another tool? Because, as I think, modern protocols, modern old protocols, low-level protocols are really vulnerable and weak. And you can ask a question, why some of them haven't been hacked yet? I think there are 2 problems. High costs and low availability of industrial hardware, and the lack of tools to work with physical layers of these protocols. And to hack them, you need the tool to connect and operate with the line on the lowest level to do the really bad things. You can use, of course, industrial modems, but they are very expensive and in general require specific software. Also, most of them are noisy and bound by standards. For example, some standard says no more than 2 masters on the line, and the modem won't allow you to become a 3rd master on the line. So I think we need some tool to hack these protocols, and I've developed one. My first try to develop such tool was done while I make my heart research. I've made an Arduino shield for heart, but it has some problems. It was noisy, exposed to high voltage bursts that are usually in industrial low-level data lines. It supported only HART protocol and was hard to extend. Also, I thought that it would be cool to have an autonomous device that can be powered from the data line itself and remotely controlled. So I've summarized all ideas in one list. The list is on the slide, and I start the development, and this is how ICSCorsair was born. The ICSCorsair is a board that could be used for attack and audit ICS low-level protocols network and attack high levels of such ICS infrastructures, of course. In next few slides, you will see development prototypes, and then I show you features of the board. On this slide, you can see very first prototype. It has really weird power supply scheme, and I've tried to fix it, putting the very big capacitor on the board, but it won't work. So I don't like this one and move to the next prototype. The second prototype has improved power source circuit and has a passive bandpass filter for HART for more clear signal. Unfortunately, some errors were made in PCB design, and this prototype never has been soldered and never worked. And this version, the third version, is the first really working prototype. The bandpass filter was moved to the microcontroller, and I've changed power isolation module. And the latest version is shown on this slide. It has few changes. Main improvements were made in HART modulator and power isolation circuits. Why did we call it ICSCorsair? F4U Corsair was a World War II US and Royal Air Forces fighter, scout, fighter bomber. It has a great speed by that times and could be armed with guns, rockets and bombs. It was a really multi-purpose plane, and in some countries it was in service till 1980. ICSCorsair is also a multi-purpose attack tool armed with many features, but for attacking ICS infrastructures. Let's look closer to the board. It has a USB connector and an XB slot. With these things you can interact with the board via wired over USB or wireless over XB card, over Bluetooth, Wi-Fi or other XB card. Also it has a power supply circuit, and that allows you to connect to almost every industrial power line. Also here we have isolated and protected from high voltage bursts RS485 circuit and HART modular. RS485 terminator resistor could be dynamically switched on and off depending on the line characteristics. The HART modem is inside MCU. The demodulating algorithm is based on the previous century HART FSK demodulator methods, and high power amplifier is added after the digital analog converter in modulator circuit. The hard task was to choose microcontroller unit for the board. After many tries, I've chosen Cypress programmable system on chip, SOC3 family. It has hardware USB support, many useful analog and digital blocks, and current version of the board could be soldered with C34 family, that is cheaper, or C38 family that has internal digital block filter, which allow to work with high-speed protocols. The board has 4 operation modes. In text to binary configuration mode, you can configure the board in terminal or using software. In HART FSK mode, board is working as a high-powered HART modem. The RS485 mode allows you to work with Modbus and Profibus DP protocols with maximum speed of 460 kilobits per second. You could change this mode at any time by sending key sequence escape M shift C and mode number in ASCII. And this is the text command mode of ICSCorsair. Using this menu, you can configure internal peripherals of the board, change low-level protocols parameters, and switch to another mode. Of course, you can jam the line from here and do other magic things. The binary commands are duplicating text mode commands, but you can use them for more comfortable work with the scripts, for example, when you're writing the Metasploit model for the board. The board has an XB slot that provides remote access. There is no difference between when you're accessing the board over USB or over XB slot card. And also, you can use such XB cards as Bluetooth, B, Wi-Fi, or RF cards, and every XB card needs some start sequence to initialize, and you could write this sequence to the EEPROM via binary or text configuration mode, and the board will be ready to attack right after the startup. For future support of other industrial protocols, I've added an expansion slot to the board. It has I2C, multiple GP and analog pins, power, and isolated ground and ground, and could be used, for example, for support Manchester bus power protocols. ICSCorsair can be used as a standalone modem, HART or RS485. Also, additional software is available in GitHub repository, such as helper Ruby scripts and Metasploit models. Also, mobile application for smartphones and tablets is in development now. Here is an example of ICSCorsair additional software. You can see HART sniffer script on this slide. If you connect the board to the current loop and run this script, then you can use it to see the content of HART packets that are flowing between field devices on the line. And also, I'm currently working on a mobile application. I'm not a very good mobile developer, rather I'm a very bad mobile developer, so the work is very slow, and any help is highly appreciated. It will be in C# using Xamarin framework, hopefully work on Android and iOS platforms. With this application, you could do audit and attack HART, Modbus, and Profibus networks using your smartphone or tablet and Bluetooth or Wi-Fi connection to the board with XP card. Okay, very sorry for such long prologue. Now we're almost ready to explain what was happened in the demo, but I need a few, especially 4 slides of theory before we move to the exploit details. FieldCare, the software that was shown in the demo, is a plant asset management software tool for managing plant asset. PAS systems lie on the upper medium levels of ICS and are integrated with manufacturing execution system and ERP systems. Most solutions are based on the FDT DTM standard. The FDT synthesizes communication and configuration interface between field devices and host systems, and DTM provides the unified structure for accessing device parameters, configuring them, using them, diagnosing problems. FDT frame application allows engineers to load and create hierarchies of DTM device drivers and user interfaces. How this works. Now, we have a frame application. In our demo, it was a FieldCare. It has several COM containers inside, and every device has a device DTM COM component, and every modem or gateway has a COM DTM component. It's a hierarchy of such components that integrates inside the frame application. The internal architecture of FDT DTM is a bit complex, but the most important thing here, I don't know, do you see this or not, it's the XML messages. The XML data is the core of the PAS and FDT DTM specifications. And when I see XML, I want to hack it immediately. Here is the screenshot of FieldCare, the typical PAS system. You could see this system in the demo. In terms of FDT DTM, it's a frame application. We used vulnerabilities of it to get a shell on SAP server. On the left part of the screenshot, you can see the industrial facility hierarchy. On the right part, it's a DTM component for the specific transmitter. And the last theory slide for today. I hope you don't get very bored. Are you? Let's talk a bit about HART addressing schemes. In general, HART uses polling ID as a network layer address and unique ID as a physical hardware layer address. Simplified, you can think about them as an IP and MAC addresses, as in usual Ethernet TCP/IP networks. But every hard field devices also has a long tag, 30 bytes long traditional ASCII address that are used as an application layer address. Simplified again, you can think about long tag as a domain name in terms of hard ICS infrastructure. And we are going to exploit right away. In PAS system, every field devices, in general every devices in the industrial facility hierarchy has a unique identifier. For hard devices, hard long tag is used as such universal identifier. And if you ask some field care developers about escaping and boundary checking, they will look like a cat on this slide. They never heard about it. Field care doesn't filter escape or provide boundary checking for hard long tags. So you can use any symbol in them with a length up to 240 bytes. It's not big. In some cases, we have only 30 bytes that we could use. And I'll explain you in a moment how we could use them. As you remember, in ICS, deep integration leads to the deep trust, so data from field care goes to the upper levels of ICS without any check, escape, or filtering. Now you're starting to understand my pain when I'm researching this and thinking how it's working in the real industrial facilities. Field care does no escaping, and FDT DTM applications are XML-based. So let's inject some XML code into COM-DTM reply and force it to load external XML scheme. We can do this by changing field device long tag or forging field devices. Using this method, we could inject a request to external XML scheme on some remote web server and send back custom XML code of any size. Let's check our theory. We will set hard long tag for some transmitter, for example, with single quote to break the parser. And you can see on the slide that field care error screen appears and detected device has empty tag. It looks like an XML parser fail, and it's XML parser fail. The consequences of such vulnerability can include server-side request forgery SSRF attacks and TLM relay attacks, XML parser denial of service using specially crafted scheme. Also, if you have unpatched and old MS XML libraries on the machine, it's often case in Russia, I don't know, in US, on the ICS machines, then it could lead to XML external entity attack, or moreover, even to remote code execution attack on XML parser. And software on ICS systems very often is unpatched. I've said it. And with SSRF, we can attack neighbor systems, for example, ERP. The attack scheme looks a bit complex, but it's highly reliable attack. At first, we are jamming the line. Normal communication breaks, and we have small pause to send packet with hard command 22. This command will change long tag in a hard transmitter EEPROM. When ICS engineer clicks on verify network, or when timeout of reconnections expires, PAS will rescan current loop through the hard gateway. Long tag data on the step 3 will go through the gateway, and the request for remote XML XSD XSchema will be created. XML parser will request it from some evil web server on the internet, for example, by temporary address, very short address, but we can change it. And then he will interpret scheme, and the remote command execution query will be sent to the SAP server. It's looking a bit complex, but I've said it's very reliable attack. I was done an experiment in 9 cases of 10. It's a successful attack. The field care almost over works as shown on this slide. Now I need to say why we're jamming the line. Remember that hard is a master slave on HAL duplex protocol, so we should not interfere our change long tag command with other line traffic. We're jamming the line, and we're getting 2 profits from it. First, we're forcing devices to follow standard and stop communication for a small amount of time. And also, we force pass system to verify devices after this time passes. And the pass system will reload long tags. Metasploit model has been created for this attack type. You could see it in the demo. It's on the GitHub repository. And on this slide, model parameters are shown. For successful attack, you will need to set target device address. You need a specially crafted long tag, 32 bytes long if you use a real transmitter. But you can forge it. I will show how. And the line jam time. For successful attack, I suggest you to use 15-20 seconds of time. It gives high reliableness. The long tag problem occurs when you use real transmitter. Long tag should not be longer than 32 bytes. Remember that this is old protocols, lower speeds. Thus, you can use only 6 symbols domain name for this attack. However, there are tons of such domains available for registration. You can register them all to prevent such types of attack. And the other solution is to forge the hard device, to man in the middle the hard transmitter and emulate it with ICSCorsair. We will talk about it in a moment. But first, I should show you the external XML scheme code that is downloaded by pass from the remote server. It's use old and good technique, classic technique. We're using FTP common script to get netcat from remote server, establish a reverse shell connection, and sub-remote command execution through HTTP GET query was discovered by Dmitry Chestuhin of ERP Scan less than 2 years ago. However, here should be any such vulnerability in ERP systems. There are more of them, of such type vulnerabilities. You can use them. Let's review another attack on field care. Lack of filtration causes many problems, and let's see how we get XSS through hard, XSS through analog protocol. Field care has an external condition monitoring component that allows to access infrastructure state through the web browser. And as you remember, field care does no escaping. We know that single quote will break XML password, but XSS attack, we can make it with double quotes. The field care condition monitoring component is shown on this slide. It looks like this. And this is the page source of the main page. Note that the long tag ABB1 is inserted into out and title parameters. And if field care does no escaping, we could try to make XSS based on the onload event, onload JavaScript event here. It's very simple. The attack scheme is the same. We jam the line, change transmitter's long tag, wait while data go through the field care to the field care monitoring, where XSS will occur. Remember that if we need to inject JavaScript code with length greater than 32 bytes, we need to make a man-in-the-middle attack or forge attack on the transmitter and emulate it. That's because field care supports long tag length up to 200 bytes and breaks the hard standard, and real hard transmitters doesn't suspect to such bug or such feature. And here we have our XSS through analog industrial protocols. And let's return to long tag problem again. We've got XSS, this is cool, but 32 bytes is enough just for simple alert 111 proof of concept, but not enough for real JavaScript payloads. However, Andres and House software developers has take care about this, and field care accepts invalid long tag packets with length up to 200 bytes. Sorry. All we need is to forge a CS device, but before this, we need to break communication between master and the original slave device. We need something like MITM hard transmitter. In the next slides, I will show how to do this. So let's start. Here we have normal communication process between pass and hard transmitter, and attacker could sniff the traffic to understand what the hard unique ID and polling ID of the forging device. Then the attacker will jam the line, and master detects the fault, and according to standard, it stops the transmission for some time. That gives the attacker a small amount of time to act as a master and send R2 command change your polling ID to 9 to the slave device, and you can see this on the picture. Now R2 has polling ID set to 9, and when the master wake up after the fault, he will begin repairing with device again, so he will send hard command 0 to determine slave unique ID for polling ID equals to 1. But R2 has polling ID 9, so it won't answer, no collision will occur, and now attacker can pretend that he has polling ID 1 and he will answer on command with his unique ID. From this time, master speaks to attacker and he thinks that he speaks with R2. Now attacker can forge any hard packets and the goal of attack is reached. However, you may think that it's hard, but I've made things simple and created special Ruby gem hard parser that is proposed to making emulation of hard devices, to forging them. All you need is to sniff the line, capture some real transmitter responses, and then add them to the emulator in the case when Ruby construction, and you are ready to forge the device. As you can see, the code is very simple, just the values of the hard parameters. Now, the last part of the talk, risk mitigations. I've discovered that vulnerabilities about more than a year ago, and Anderson Hauser, for a year, ignores me. So, sorry, Anderson Hauser, I'm full disclosure to you. And I've done this because some other PAS software and DTM components are vulnerable to maybe a bit different, but same by the characteristics, XML injections. I'm waiting while vendors will fix it, but you should know the possible steps of mitigation. You should enclose pass server with IPS or application layer firewall to prevent the expanding of attack. The physical security, again physical security, and again physical security should be implemented for all your transmitters and current loop lines on the network. And maybe someone should develop low-level IDS or low-level gateway like the car engineers implement in the CAN buses. Divide the good packets from the bad packets. And still no such solution, and I think it sounds like a good startup idea. I'm giving it to you. I hope you will develop, someone will develop such thing. I should mention other attacks. It's maybe forging Modbus devices, sniffing Profibus DP bus, denial of service attacks, for example, attack on Enormia Pro configuration software through the very long hard packet. And a conclusion at last. As you can see, ICSCorsair provides tools and abilities for attacking hard and Modbus industrial protocols. And modern ICS infrastructures are very fragile on the low-level protocols, and physical security should be to-do item number 1. Also, Captain Obvious is reporting ICS industry needs to move to the modern technologies, for example, Ethernet, or embed security mechanism in the current future versions of low-level industrial protocols, or made some specific hardware and software to prevent such types of attack. The future work to do is shown on the screen, and I also should mention that ICSCorsair is an open source hardware, so we really need community help in improving its hardware, firmware, software. Your help will be very great. The work on this research was very, very hard, and it couldn't be successful without the help of people listed on this slide. I would like especially to thank Svetlana Cherkasova for field care reverse engineering, Sergey Piperam5 for helping in circuit and PCB design, Alexander Malinovsky for help in creating the first version of the board, Solar Designer, aka Alexander Pislyak, for many bright ideas, and ERP Scan Company for help and support, Dmitry Chestuhin for especially Dmitry Chestuhin for the marvelous remote command execution in SAP that I have used in the demo, and other people and companies. Here are the links. You can get ICS Corsair hardware, firmware, software, binaries, bill of materials from the GitHub. The hard parser repository is separated, and you can order PCB at the Park. And thanks for listening. Two more things to say before I finish. First, I brought here several ICS Corsair PCBs. So if you want to play with it, and if you know how to solder, I can give it to you for free. And you can ask me after the talk. And I don't want to bring them back to Russia because explaining to customs officers of Russia and US what this is and why I should bring it to Las Vegas was rather nervous. I don't want to repeat this quest. Also, I'm very sorry for torturing you with my really bad English and awful Russian accent. Thanks for patience, and sorry for that. Now, if you have any questions, I'm ready to answer. Thanks again.
Hi. I was wondering, do any of these devices, the RCSs, do they connect to multiple industrial lines? And is the tool that you created able to communicate with the dual line?
I don't hear. Can you please a bit?
So the RCS
Yes.
devices, I was wondering, do they connect to more than one just industrial line? And
Yeah.
can your device communicate with those industrial lines, like each
Yes.
one individually?
You could connect to the line. The lines can be outside the ICS, so it's possible to find such thing. Eventually, on the audits of ICS infrastructure in CIS countries, I found such lines and used them for attacking.
Okay, thank you.
I'm just curious, have you looked at BACnet at all, or any devices that are doing, or I don't know if you know what BACnet is. It's basically industrial control systems like BAS systems and stuff and SCADA going over IP. Have you looked at any devices or compromising them that do Modbus to BACnet?
It's a hard question because I've tried the same attacks with Modbus devices as you could probably, in most cases, be succeed, but I didn't research Modbus and Profibus DTM components. That's the next research. However, now we're developing, along with Svetlana Cherkasova, a new dynamic fuzzer for the DTM components. Maybe we will present it on Black Hat Europe if we be accepted at the CFP, or you can see this talk on the Zero Nights in Moscow this November.
I think I'll be able to make it to Moscow, but I'll try and find it online. Thanks.
Great lecture. Thank you very much for giving it. I had a couple of questions. You gave a couple of examples where a signal could be presented to the remote device or to the server that kind of confused it for a second and it had to kind of reorient itself. Is that one of the ways of doing a DDoS attack or denial of service attack against these SCADA networks? And how effective would that be? How long could you hold up basically presenting some sort of signal that basically overwhelms the network or confuses the network? How long could you hold that? How effective would it be?
As I've said, to make an attack, you need only 15-20 minutes for high reliableness. But if you need to disturb the line at all, you just need 4 or 5 minutes. And after that, most software getting crazy, most transmitters getting crazy and will freeze, and you will totally destroy all the ICS infrastructure on this hard protocol line. This may be more dangerous than hacking SAP through it.
Thank you very much.
Thank you. Thank you very much.